Our solar system contains 8 planets. Mercury, a tiny rocky sphere slightly larger than the Moon. Venus, nearly Earth's twin in size but with a lethal atmosphere. Earth, the only planet we know carries life. Mars, a red desert with a thin atmosphere and traces of ancient water. Jupiter, a gas giant so large that all the other planets in the solar system could fit inside it with room to spare. Saturn, with its rings visible through an amateur telescope. Uranus and Neptune, ice giants at the far reaches. This was our home. Everything we knew about planets for most of human history. In 1992, we detected the first planet beyond our solar system, an exoplanet, a planet orbiting another star. Since then, we have found more than 5,000, and among them, objects that challenge the very concept of planet, worlds so enormous that our largest planets look like peas beside them. Gas giants whose atmospheres extend hundreds of thousands of kilometers. Objects occupying the space between our understanding of planets and our understanding of stars. Among them, the largest planets we have ever found. Tonight we are going to talk about them honestly, not just about impressive numbers, though the numbers here are genuinely impressive, but about what these objects tell us about how planetary systems form, about the diversity of worlds in the universe, and about how unusual or ordinary our own solar system looks against this backdrop. If the night is long, stay. Let us begin with context, with understanding what makes an object large when we are talking about planets. Planets are classified by several parameters. Mass, the amount of matter the object contains. Radius, the physical size. Density, mass divided by volume, which speaks to composition. Formation mechanism, from what and how the object formed. For planets in our solar system, there is a convenient reference system. Jupiter, the largest of our planets. Its mass is about 318 Earth masses. Its radius is about 11 Earth radii. It is so large that the solar system, in terms of body masses, is essentially the Sun plus Jupiter and everything else. When discussing exoplanets, astronomers often use Jupiter masses and Jupiter radii as units. This is useful because the largest exoplanets significantly exceed Jupiter. But first, an important question. Where does a planet end and a star begin? Stars shine because their cores undergo nuclear fusion. Hydrogen converts to helium with the release of enormous energy. This requires a certain minimum mass, sufficient for gravitational pressure in the core to create conditions for fusion to begin. The minimum mass for a star is about 80 Jupiter masses. An object lighter than this cannot ignite hydrogen fusion and does not become a star in the ordinary sense. Between planets and stars, there exists an intermediate class of objects, brown dwarfs. They are too massive to be planets, above roughly 13 Jupiter masses, but insufficiently massive to sustain long-term hydrogen fusion, below about 80 Jupiter masses. Some of them can briefly burn deuterium, a lighter isotope of hydrogen, but this ends quickly. The boundary between a very massive planet and a brown dwarf is a matter of scientific debate. The approximate boundary of 13 Jupiter masses is currently accepted. Objects heavier than this are often called brown dwarfs or stellar-type objects. Among planets proper, giant gas planets in the range of 1 to 13 Jupiter masses are called hot Jupiters if close to the star, or simply gas giants if farther out. Let us now talk about the specific record holders, about the planets that are the largest ever discovered and what exactly makes them so. ROXS 42BB, discovered in 2013, located in the young Rho Ophiuchi cluster about 140 light-years away. Mass, about 9 Jupiter masses. Radius, about 2.5 Jupiter radii. Wait, 9 Jupiter masses but 2.5 Jupiter radii? How can an object be larger by radius but proportionally not as heavy? The answer? This planet is extraordinarily young. The age of the ROXS42b system is about a few million years. By cosmic standards, this is almost newborn. Young gas giants are hot. They have not yet had time to cool and contract to a compact, mature state. Their atmospheres are puffed up by the heat of formation. Over time, ROXS42bb will shrink. Its radius will decrease as it cools. The surface temperature of ROXS42bb, about 1800 Kelvin. For comparison, the temperature of Jupiter's surface is about 165 Kelvin in the upper clouds. 1800 Kelvin is red-hot metal by Earth standards. This planet glows with its own thermal radiation. HAT-P-67b, discovered in 2017. Distance from us about 1,200 light-years. Mass, about 0.34 Jupiter masses. Radius, about 2.085 Jupiter radii. This is an interesting case. Mass less than half of Jupiter's, but radius more than twice Jupiter's. This is a so-called inflated hot Jupiter, a planet with a puffed-up atmosphere due to proximity to its parent star. HAT-P-67b orbits its star at a distance of only about 0.064 astronomical units. For context, Mercury, the planet closest to the Sun, is at 0.387 astronomical units. HAT-P-67b is 6 times closer to its star than Mercury is to the Sun. At such proximity to a bright, hot star, HAT-P-67 is a class F star, hotter and brighter than our Sun. The planet's atmosphere is heated to temperatures of about 2000 Kelvin. The gas expands. The planet puffs up. Worse, at these temperatures and intense stellar radiation, the planet's atmosphere is literally evaporating into space. HAT-P-67b is losing mass. Slowly but continuously, atmospheric gas stripped away by stellar wind and radiation. This phenomenon is called photoevaporation of the atmosphere. Planets of this type over time lose their atmospheres and turn into bare, rocky cores, if they have a solid core at all. WASP-79b, discovered in 2012, distance about 780 light-years, mass about 0.9 Jupiter masses, radius about 2.0 Jupiter radii, orbital period about 3.7 Earth days. WASP-79b became famous as one of the first exoplanets where the James Webb Space Telescope detected water vapor, carbon dioxide and carbon monoxide in the atmosphere, in detail unavailable before JWST. Its atmosphere is being studied as a sample hot Jupiter with exceptionally clear spectral features. The atmospheric temperature of WASP-79b, about 1716 Kelvin, one side is always facing the star, the planet is tidally locked, the other always in darkness. The temperature difference between day and night side creates extreme atmospheric flows, winds that can reach several thousand kilometers per hour. Let us now talk about the most interesting cases, about objects in the range of 10 to 13 Jupiter masses that are the most massive of what we call planets. Kappa Andromedae b, Discovered in 2012 by direct imaging, literally photographed, which itself is an outstanding achievement for an object around another star. The star Kappa Andromedae is about 170 light-years away. The planet's mass, about 13 Jupiter masses, radius, about 1.7 to 1.9 Jupiter radii. 13 Jupiter masses is exactly the boundary value between a planet and a brown dwarf. Some astronomers classify Kappa Andromedae b as a planet, others as a brown dwarf. The question remains open. What makes this object particularly interesting? Its orbit. Kappa Andromedae b orbits its star at about 1.058 astronomical units, roughly as Earth orbits the Sun. But this is not a modest Earth. This is an object 13 times heavier than Jupiter, 4,000 times heavier than Earth, on an orbit similar in distance to Earth's. The scale of the difference: if you placed Kappa Andromedae b where Earth stands, our planet would disappear as something negligible against the background of this colossus. Atmospheric temperature, about 1,700 Kelvin. This object is also young and hot. The age of the system is about 30 million years. It shines in the infrared range with its own thermal radiation, which is what allowed it to be photographed directly. Let us now talk about detection methods, because how we find these enormous objects directly affects how representative our sample is. The transit method. If a planet passes in front of its star, from our perspective, it partially blocks starlight. The star's brightness decreases slightly during the transit. The magnitude of decrease depends on the size of the planet relative to the star. The Kepler telescope and its successors used exactly this method to find thousands of exoplanets. Limitation. We can only detect planets whose orbital planes are oriented so that the transit is visible from Earth. Most orbital planes are oriented differently, and those planets we do not see. Estimates suggest transits reveal only a small fraction of existing planets. The radial velocity method, Doppler spectroscopy. A planet does not only orbit the star also wobbles slightly back and forth due to the gravitational attraction of the planet. This wobble shifts the star's spectrum. When the star moves toward us, its light slightly blue shifts. When it moves away, it red shifts. Measuring these shifts allows calculating the planet's mass and orbital period. Limitation. This method works better for massive planets close to the star. They create larger wobble. Small planets far from the star are nearly undetectable by this method. Direct imaging, literally photographing the planet. Extremely difficult. The star is millions of times brighter than the planet, and resolving them separately requires special systems to suppress starlight, coronagraphs and adaptive optics systems. Limitation. Works mainly for very young, and therefore hot, glowing in the infrared, and massive planets on large orbital separations from the star. Mature cold planets are essentially invisible by this method. Gravitational microlensing. When a massive object, a star or planetary system, passes between us and a more distant star, its gravity acts as a lens, amplifying the light of the background star. If the foreground star has planets, they create additional brief brightness peaks in the amplification curve. Limitation. A microlensing event happens once and does not repeat. The planet is discovered, but conducting additional observations of this system is practically impossible. The method is good for statistics, but not for detailed study of specific systems. The most important consequence of these limitations: our sample of exoplanets is deeply biased. We see primarily large planets close to stars. Small planets far from stars are practically inaccessible to most methods. The true distribution of planets in the universe which we reconstruct through statistical corrections for observational biases, is significantly richer and more diverse than what we directly observe. Let us now talk about hot Jupiters as a class, about what makes them so prevalent in exoplanet catalogues and how actually common they are in the universe. Hot Jupiters, gas giants with orbital periods less than 10 days, meaning very close to the star, were the first exoplanets discovered around Sun-like stars. 51 Pegasi b, discovered in 1995, a gas giant with an orbital period of about 4 days. This was a shock. Nobody expected a gas giant could exist so close to a star. In our solar system, gas giants, Jupiter and Saturn, are far from the Sun, 5.2 and 9.5 astronomical units respectively. Standard planetary formation theory predicted that gas giants can only form beyond the snow line, far enough from the star where temperatures allow ices to condense and serve as building material. This is roughly 3 to 5 astronomical units from a Sun-like star. Hot Jupiters violated this picture, not because the theory was entirely wrong, but because it did not account for migration. After the discovery of 51 Pegasi b, a picture gradually formed. Hot Jupiters form far from the star beyond the snow line, as theory predicted. But then, interaction with the protoplanetary gas disk causes them to lose angular momentum, and they migrate inward toward the star over millions of years. They end up a few hundredths of an astronomical unit from the star, significantly hotter than at formation, with puffed atmospheres under the influence of intense stellar radiation. This explains why hot Jupiters dominate catalogues. They are large, easily detected by transits. They are close to the star. Short orbital periods allow many transits to be recorded in short observation times, and their effect on stellar radial velocities is large. But hot Jupiters are rare in a statistical sense. They occur around roughly 0.5 to 1% of Sun-like stars. Most stellar systems do not have hot Jupiters. In our solar system, Jupiter remained far from the Sun. This is possibly not coincidental, but a consequence of orbital resonance with Saturn stopping its migration before it went far. This is potentially an important factor for Earth's formation and life's development. Jupiter, in its current orbit, acts as a gravitational shield, deflecting many comets and asteroids that would otherwise have bombarded the inner planets far more intensely. Let us now talk about the system that is one of the most impressive examples of large planets discovered by direct imaging, about the HR 8799 system. HR 8799, an A5 class star in the constellation Pegasus, about 130 light-years away. It is roughly 1.5 times more massive and 5 times brighter than the Sun. The age of the system is estimated at about 30 to 60 million years, young by galactic standards. In 2008, a team of astronomers led by Christian Majois published images obtained at the Keck and Gemini telescopes showing 3 planets orbiting HR 8799. This was the first direct image of a multiple planetary system around another star. In 2010, a 4th planet, even closer to the star, was discovered. The 4 planets, HR 8799b, c, d, e, are all gas giants with estimated masses of 5 to 7 Jupiter masses each. They are at distances from 14 to 68 astronomical units from the star, significantly farther than our gas giants from the Sun. Jupiter is at 5.2 astronomical units, Saturn at 9.5 astronomical units. All 4 HR 8799 planets are farther than this. The HR 8799 system is a unique laboratory for understanding planetary formation for several reasons. First, Direct images exist in multiple epochs. The planets have been photographed repeatedly since 2008. This allows direct observation of their orbital motion. In the accumulated collection of images, you can literally see the planets moving around the star, not calculating their orbits from indirect signs, but seeing their motion in real time. Very slow, of course. The orbital period of the outer planet, HR 8799b, is about 460 years. Second, all 4 planets are close in mass to each other. This is atypical. In our system, Jupiter is 3 times heavier than Saturn and more than 20 times heavier than Uranus and Neptune. The 4 HR 8799 planets form a more uniform quartet. Third, their orbits are at or near orbital resonances with each other. This means the system is gravitationally coupled. The orbital periods of the planets are related as small whole numbers. Such resonances stabilize orbits and prevent chaotic interactions. The atmospheres of the HR 8799 planets have been studied through spectroscopy, measuring the spectra of their thermal radiation. Water vapor, methane, carbon monoxide, carbon dioxide have been detected. Temperatures around 1000 to 1200 Kelvin, hot for planets, but significantly cooler than hot Jupiter's, since they are far from their star and their heat is mainly residual heat of formation. The HR 8799 system is important because it suggests a different gas giant formation mechanism than hot Jupiter's. Hot Jupiter's probably migrated inward. The HR 8799 planets are far from the star. There was no inward migration. They formed where they currently are. This means that beyond the snow line, multiple gas giants can form simultaneously if there is enough material in the protoplanetary disk. Our solar system, with 4 gas and ice giants, Jupiter, Saturn, Uranus, Neptune, is an example of this mechanism. HR 8799, with 4 more massive planets significantly farther from the star, an even more extreme example. Let us now talk about the specific size record, about the planet that by its radius is the most extreme known object in the planetary catalogue. WASP 17b, discovered in 2009. Distance about 1,000 light-years in the constellation Scorpius. Mass about 0.49 Jupiter masses. Radius about 1.89 Jupiter radii. Notable: mass roughly half of Jupiter's, but in volume this planet is about 7 times larger than Jupiter. Its average density is about 0.06 grams per cubic centimetre, less than 1/20th of the density of water. For comparison, the density of water is 1 gram per cubic centimetre. The density of air at sea level is about 0.0013 grams per cubic centimetre. WASP 17b is about 50 times denser than air, a very rarefied gas. If you could find a sufficiently large ocean, WASP 17b would float in it like a cork. Its average density is 94% lower than the density of water. The orbital period of WASP 17b about 3.73 Earth days. And what is especially interesting, the orbit is retrograde. The planet moves in the direction opposite to the star's rotation. Retrograde orbits of hot Jupiters are a serious challenge for formation theories. Planets form from a rotating disk, and therefore should rotate in the same direction as the disk, meaning the same direction the star rotates. A retrograde orbit means something changed the planet's orbit radically. The most plausible explanation, the Kozai-Lidov mechanism. If there is a third massive object in the system, another star, another gas giant, on a distant inclined orbit, its gravitational influence can gradually rock the orbit of the inner planet. The orbit becomes increasingly eccentric and increasingly inclined. When the planet approaches the star closely at perihelion, tidal interactions with the star circularize the orbit. The planet ends up on a circular orbit close to the star, but inclined or even retrograde relative to the star's rotation. WASP-17b was studied by the James Webb Space Telescope in 2023, and this study became one of the most significant for the atmospheric science of exoplanets. JWST detected silicon dioxide in the form of crystalline grains in the atmosphere of WASP-17b, quartz crystals floating in the atmosphere. This was the first direct detection of silicate crystals in an exoplanet atmosphere. Quartz clouds. Clouds consisting of tiny quartz crystals suspended in hot gas. This is not a metaphor or analogy. This is literally what JWST measured. Let us now talk about WASP-12b and what happens to a gas giant too close to its star. WASP-12b, discovered in 2008. Distance about 1,400 light-years. Mass about 1.47 Jupiter masses. Radius about 1.79 Jupiter radii. Orbital period 1.09 Earth days, less than 26 hours. Distance from the star about 0.023 astronomical units. This is roughly 1/16 the distance from Mercury to the Sun. At such extreme proximity, WASP-12b is inside the Roche limit of its star. The Roche limit is the distance from the star inside which tidal forces from the star exceed the planet's own self-gravity. Simply put, the star is literally pulling the outer layers of the planet toward itself. WASP-12b is losing mass. Its atmosphere flows onto the star through the L1 Lagrange point, the point of gravitational equilibrium between the planet and the star. This process is called mass transfer or mass overflow. The rate of mass loss is estimated at several times 10 to the 11th power grams per second. This is an enormous amount, about several 100,000 tons per second. In 1 year, WASP-12b loses about 3 times 10 to the 18th power grams. At the current rate, the planet will be completely destroyed in roughly 10 million years. By geological standards, in a moment. The orbit of WASP-12b is also degrading. Tidal interactions between the planet and the star transfer orbital angular momentum. The orbit slowly contracts. The planet spirals inward toward the star. Observations have confirmed this. The orbital period of WASP-12b decreases by about 29 milliseconds per year. A small number, but measurable and significant. We are watching the death of a planet in slow motion. WASP-12b is not a stable system. It is a transitional moment in the evolution of the system. In millions of years, this planet will cease to exist. Its material will merge with the star. What we observe now is the final act of a long history that began with the formation of a gas giant far from the star, continued with inward migration, and ends in catastrophic finale. This is one of the most dramatic examples of how planetary systems are not eternal static constructions. They evolve, they change. Planets can move, collide, be destroyed. Let us now talk about something specific that connects all these enormous planets with the question of life, about whether moons of gas giants can be habitable. In our solar system, the moons of gas giants, Europa, Ganymede, Callisto around Jupiter, Enceladus and Titan around Saturn, are among the most promising places in the solar system for searching for life. Tidal heating maintains liquid oceans under the icy surfaces of Europa and Enceladus. Can moons of exoplanets, including enormous hot Jupiters, be habitable? Theoretically, yes. If a hot Jupiter has moons of sufficient size, and if the distance from the star is in the habitable zone by temperature, and if the moon has enough water, there are no fundamental prohibitions on life. But hot Jupiters are generally too close to the star. The habitable zone for a Sun-like star is roughly 0.8 to 1.5 astronomical units. Hot Jupiters at 0.02 to 0.05 astronomical units, far inside this. Any moon at such distance would be heated far above the possibility of liquid water. But gas giants on more distant orbits in the habitable zone could theoretically have habitable moons. In our solar system, Jupiter is outside the Sun's habitable zone, too far. But around more distant stars, the habitable zone is also farther, and a gas giant in the habitable zone of a more distant star is not forbidden. Moreover, a gas giant in the habitable zone with its tidal heating of moons could create more stable conditions for life on its moons than an orbit without a gas giant. Tidal heating maintains geological activity. Geological activity provides material cycling. Material cycling supports a potentially viable environment for billions of years. We have not detected such moons directly yet. The technology for detecting exomoons, moons around exoplanets, is only beginning to develop. A possible candidate, Kepler 1625b/I, was identified in 2018, but its reality is disputed. Nevertheless, this direction is being actively developed. If life exists beyond Earth, a moon of a massive gas giant in a habitable zone is one of the most promising places to search for it. Let us now talk about the most exotic and conceptually challenging category of large planets, about rogue planets. Most planets we observe orbit stars. This is expected. Planets form in protoplanetary disks around forming stars. But planets exist that do not orbit any star. They travel alone through interstellar space, rogue planets or free-floating planets. How did they get there? Several mechanisms. First, gravitational ejection from planetary systems. If in a forming system several gas giants interact gravitationally, one of them can receive an impulse sufficient to leave the system entirely. This is not a hypothetical scenario. Computer simulations of planetary system formation show that ejection of gas giants is a common event. Second, formation outside a planetary system. Stars form from collapsing molecular clouds. Sometimes the cloud fragments into objects of different masses. Large fragments become stars, small fragments, below the threshold for igniting hydrogen fusion, become brown dwarfs or very massive planets. These objects can form without a host star. How many rogue planets exist? Estimates vary greatly depending on method. Microlensing as a detection method allows detecting objects not bound to a star. Various studies have given estimates of 1 to several rogue planets per star in the galaxy. If these estimates are correct, the Milky Way may contain hundreds of billions or even trillions of rogue planets, possibly more than there are stars. These are astonishing numbers, and they raise the question, is there life on rogue planets? At first glance, no. Without a star, there is no sunlight. Without light, there is no photosynthesis, no energy to maintain a warm biosphere. But there is a nuance. A sufficiently massive rogue planet, especially a young one still hot, may have sufficient heat flow from internal layers to maintain liquid water beneath an icy surface, like on Europa, but without Jupiter. Heat from radioactive decay in the core and from residual heat of formation. This is not a comfortable environment for life in our understanding. But life in our understanding is possibly not the only type of life possible in nature. Let us now talk about how studying the largest planets changes our understanding of planetary system formation, about what these objects tell us about how nature builds worlds. Before the discovery of exoplanets, the formation of our solar system was treated as something of a model case. Rocky planets inside the snowline, gas giants outside. Planets with near-circular orbits in one plane. A stable system formed 4.6 billion years ago and little changed since. Exoplanets destroyed this narrative. We found gas giants closer to their star than Mercury. We found planets on orbits with enormous eccentricity, elongated, swinging far from the star, then rushing back toward it. We found planets on retrograde orbits, moving in the opposite direction relative to the star's rotation. We found planets on polar orbits. We found systems with multiple planets in orbital resonance. We found systems where there is nothing resembling our solar system. It turned out that our solar system is not the model case, but just one of many possible outcomes, and judging by the statistics, not the most common one. The most common type of planets, according to the Kepler telescope, is mini-Neptunes and super-Earths, planets with radii from 1.25 to 4 Earth radii. Nothing like this in our solar system. We go directly from Earth, 1 radius, to Neptune, about 3.9 radii. No intermediate-size planets. This means our solar system is in some sense unusual. We lack the most common type of planet. Why? Unknown. Possibly connected to Jupiter's migration history. Possibly to the composition of the protoplanetary disk from which our system formed. Possibly simply a statistical fluctuation. But the largest exoplanets, enormous hot Jupiters with radii twice Jupiter or more, remind us that nature can build planets significantly larger than anything in our system. That our Jupiter is not the limit of the possible. That worlds exist that make Jupiter look small. Let us now talk about the interior structure of the largest gas planets, about what their internal structure looks like and what it tells us about extreme states of matter. Inside Jupiter, with which we compare all exoplanets, as pressure increases, hydrogen goes through several phase transitions. In the outer layers, molecular hydrogen, H2, hydrogen in the form of 2-atom molecules, familiar chemistry. Deeper, pressure increases to megabars, 1 million atmospheres. At such pressure, hydrogen molecules dissociate, atoms separate. Further, at even higher pressure of about 1 to 2 megabars, electrons separate from nuclei. Hydrogen transitions to a metallic state. Metallic hydrogen is an electrical conductor. It is from metallic hydrogen that Jupiter's magnetic field is generated. In the largest exoplanets, objects of 5 to 10 Jupiter masses, the pressure and temperature in the center are significantly higher. The central pressure can reach several tens of megabars. Under these conditions, metallic hydrogen enters regimes of even more exotic states, possibly a state that is neither solid, nor liquid, nor gaseous in the ordinary sense. The most massive gas giants should have magnetic fields so strong they can create significant magnetic interactions with their stars. Some observational signs of such interactions, enhancement of stellar chromospheric activity in a phase coinciding with the orbital position of the planet, have been detected for several hot Jupiters. These are planets that interact with their stars not just gravitationally and through tides, but magnetically. A completely new type of planet-star interaction without analogue in our solar system. Let us now talk about the specific stars on the real night sky that host the largest known planets, about where to look. Most host stars of the largest exoplanets are too far away to see with the naked eye. HAT-P-67, which hosts the enormous HAT-P-67b, about 1,300 light-years, too faint for the naked eye. But some systems with large planets are close enough. Tau Boötis, a star in the constellation Boötes, distance about 51 light-years, visible to the naked eye, magnitude 4.5, has a hot Jupiter Tau Boötis b, with mass about 5.95 Jupiter masses and orbital period about 3.3 days. Discovered in 1996, one of the first hot Jupiters in the catalogue. When you look at Tau Boötis with the naked eye, you see a star with a gas giant 6 times heavier than Jupiter, orbiting it faster than a week. This world is 51 light-years away, by astronomical standards right next door. 51 Pegasi, in the constellation Pegasus. Distance about 51 light-years, visible to the naked eye, magnitude 5.5, faintly visible under good skies. This is the star of the first discovered hot Jupiter, 51 Pegasi b, also known as Dimidium or Bellerophon. The planet's mass about 0.47 Jupiter masses, orbital period about 4.23 days. The 1995 discovery permanently changed planetary astrophysics. The constellation Pegasus is well visible in summer and autumn from most inhabited points on Earth. The square of Pegasus, a prominent asterism of 4 stars. 51 Pegasi is slightly to the west and south of this square. Too faint for the naked eye from city skies, easily seen in binoculars. These are stars you can find on the real night sky, knowing they carry systems with enormous gas giants. That behind all the abstraction of our conversations about Jupiter masses and orbital periods, there are specific places on a specific sky. Let us now talk about the next generation of instruments and what discoveries await in the coming 10 to 20 years. The James Webb Space Telescope is already operating and already revolutionizing atmospheric spectroscopy of exoplanets. Its infrared sensitivity allows detecting molecular signatures in exoplanet atmospheres with unprecedented precision. In 2022 to 2023, JWST already detected CO2 in the atmosphere of WASP-39b, sulfur dioxide in the same system indicating photochemistry in the atmosphere, quartz crystals in the atmosphere of WASP-17b, hints of methane and CO2 in the atmosphere of planet K218b, a planet in the habitable zone. Detailed temperature maps of several hot Jupiters through phase curves. The extremely large telescope, ELT, under construction in Chile. Mirror diameter of 39 meters. Expected start of observations around 2028. Its capabilities in direct planet imaging significantly exceed anything currently existing. It will be able to directly image planets at much smaller separations from the star than current instruments, approaching the ability to directly image Earth-type planets around the nearest stars. The Nancy Grace Roman Space Telescope, a NASA space telescope planned for launch in the mid-2020s. It will be equipped with a coronagraph for direct planet imaging. Its main exoplanet task, microlensing for detecting rogue planets and moderate-sized planets around distant stars. The Plato mission from the European Space Agency, a space telescope planned for launch in 2026. Primary goal: finding Earth-type planets in habitable zones of Sun-like stars through transits, with subsequent precise mass measurement through radial velocities. Plato should find dozens or hundreds of Earth-type planets around nearby bright stars, allowing their detailed study. Together, these instruments will give us an exoplanet catalogue significantly more complete and detailed than the current one. We will get statistics on the population of the largest planets across the full range of orbits and around all types of stars. We will get detailed atmospheric profiles of hundreds of planets instead of dozens. We will get direct images of planets around nearby stars. The next 20 years in exoplanet astrophysics promise to be the most discovery-rich in the history of the field. Let us now talk about what the history of exoplanet discovery specifically tells us about the pace of science in this field, about how we went from 0 to 5,000 confirmed planets in 29 years. 1992, first planets discovered, but around a pulsar, a dead star, not a sun-like star. Interesting, but not what theorists had imagined. 1995, 51 Pegasi b, the first planet around a sun-like star. The shock, the disbelief, the confirmation, the revolution. 1999, first system with multiple planets, Upsilon Andromedae. First transiting hot Jupiter, HD 209458b, allowing for the first time to measure a planetary radius from outside our solar system. 2003, first direct detection of light from an exoplanet, HD 209458b, and TRES-1 in secondary eclipse by Spitzer. 2008, first direct images of exoplanets, HR 8799b-c-d, Fomalhaut b. 2009, Kepler launched. Everything accelerated. 2014, Kepler 186f, first Earth-sized planet in a habitable zone of another star. 2015, 1,000 confirmed exoplanets. Then 2,000. Then 3,000. 2016, Proxima Centauri b, a potentially habitable planet around the nearest star to our Sun. 2019, Nobel Prize for Didier Queloz and Michel Mayor for 51 Pegasi b, confirmation that this was the discovery that opened a new era. 2021, over 4,500 confirmed exoplanets. 2022, JWST begins science operations. First detailed atmospheric spectra at new levels of precision. Quartz clouds, sulfur dioxide photochemistry. 2024, over 5,500 confirmed exoplanets. 29 years, 0 to 5,000. A revolution that is still accelerating. The largest planets are where this revolution began, with 51 Pegasi b, itself a hot Jupiter. They're where the largest surprises came, planets with radii twice Jupiter's, with densities lower than water, with iron rain and quartz clouds, with orbital periods shorter than Earth days. They will not be the last surprise. Let us talk about something that brings the abstract numbers into concrete physical reality, about what it would actually be like to be in orbit around the largest known planets, and what you would see. Imagine you are in a spacecraft in orbit around HAT-P-67b, the inflated hot Jupiter with a radius almost 3 times Jupiter's. You are at an altitude of perhaps 50,000 kilometers above the cloud tops. This is inside the Hill sphere, the region where the planet's gravity dominates over the stars, and just far enough to maintain a stable orbit. What you would see. The planet below you is enormous. Even at 50,000 kilometers altitude, significantly farther than the ISS is from Earth, the planet fills most of your field of view. Its apparent angular diameter is roughly comparable to looking at Earth from low orbit. The planet is so large that even from this distance it dominates the visual field. The color is not like Jupiter. At temperatures near 2000 Kelvin, the upper atmosphere glows. Not brightly enough to light the ship, but a faint orange-red thermal glow at the limb where you look through a thicker atmospheric column at a low angle. The visual appearance is something between a dim ember and a very dark red sunset. The cloud structure is visible but wrong. Not the elegant banding of Jupiter, because the planet is tidally locked. On the day side, below you, the cloud patterns are driven by the brutal, direct stellar heating. On the night side, the clouds are different, cooler, potentially with different condensates. The terminator, the line between day and night, is a zone of rapid transition, with cloud structures that don't look like anything in our solar system. The star is very close. At 0.064 astronomical units, the star subtends an angle many times larger than our Sun appears from Earth. It is overwhelming, not something you look at. It is a furnace filling a significant arc of sky. The light is intense. The radiation environment at your position is extreme. The spacecraft's radiation shielding is working continuously. The planet's magnetic field is strong, stronger than Jupiter's potentially. Charged particles spiral along field lines into the polar regions. At the poles, perhaps, auroras, produced not just by the stellar wind, but by the intense magnetic interaction between the planet and the star itself. There is no moon. Hot Jupiters do not have moons. Any moon that once existed was either ejected during the inward migration or was lost to tidal forces and stellar radiation over the lifetime of the system. It is a profoundly alien view. More alien than anything in our solar system. More alien than the surface of Io or the undersurface ocean of Europa. This is a world with no analogue in human experience. A gas world glowing faintly in its own heat. A world where the day-night difference is not one of temperature, but of kind. The day side is an inferno. The night side is a darkness where iron rain falls and silicate clouds drift. Now imagine the same exercise at TOI-2109b, the planet with a 16-hour orbital period. At this orbital period, the planet is moving around its star at about 300 kilometers per second. From your orbital position above it, the star appears to move visibly. You can watch it track across the sky as the planet completes its rapid orbit. One complete orbit during a single sleeping period. The tidal distortion of the planet is visible. TOI-2109b is being gravitationally squeezed into a slightly elongated shape by the star's tidal forces. The planet is not quite spherical. the substellar point is closer to the star, meaning the planet's surface is slightly pulled in that direction. The atmospheric temperature gradient from the day side to the night side is the steepest of any known planet, about 3000 Kelvin difference. The terminator is not a gradual transition, but a sharp boundary. On one side, 3630 Kelvin temperatures, glowing atmosphere, stripped silicates. On the other side, relative darkness, extreme cold by comparison, possibly condensing exotic minerals. The planet is losing mass even as you watch. Not visibly. The mass loss rate is large in stellar terms, but negligible in human time perception. But the instruments would show it, a thin stream of atmospheric gas flowing from the day side toward the star through the L1 Lagrange point, a gossamer thread of evaporating planet being drawn toward the stellar surface. You are orbiting an object in the process of being destroyed, on a timescale of millions of years, an eye blink in cosmic time. Both of these views, from orbit around HAT-P-67b and from orbit around TOI-2109b, are physically possible given the planetary parameters we have measured. They are not science fiction. They are the logical extrapolation of the data. Let us now talk about a specific topic that illuminates why the largest planets are scientifically valuable beyond their impressiveness, about what they tell us about the interior structure of gas planets in general. Measuring the interior structure of a gas planet directly is impossible. We cannot send a probe into the deep interior. The pressures and temperatures destroy any conceivable instrumentation long before reaching significant depth. What we can do is use the gravitational field of the planet as a probe of its interior mass distribution. A planet that is uniformly mixed has a specific gravitational field. A planet with a dense rocky core has a different gravitational field. A planet with a gradual density gradient has yet another. For planets in our solar system, we can measure the gravitational field in extraordinary detail by tracking the orbits of spacecraft flying through the system. Juno at Jupiter and Cassini at Saturn have provided gravitational field measurements precise enough to significantly constrain the interior structure. For exoplanets, this direct approach is not available. But there is an analogue, the relationship between mass and radius. For a planet of given composition and temperature, there is a specific radius predicted by theory for each mass. Rocky planets follow one mass-radius relationship. Planets with hydrogen-helium envelopes follow another. Planets with thick water-ice mantles follow another. By measuring both the mass, from radial velocity, and radius, from transit depth, of an exoplanet, we can place it on a mass-radius diagram and compare to theoretical predictions. This tells us what the planet is made of, at least in broad terms. The hot Jupiters and large exoplanets create an interesting problem on this diagram. Many of them have measured radii significantly larger than theoretical models predict for their masses. This is the inflation problem we discussed earlier. But the inflation problem is scientifically valuable precisely because it forces us to understand what additional physics is required. What process is depositing energy into the deep atmosphere to maintain the inflated radius? This is a genuine open question whose resolution will deepen our understanding of gas giant interiors in general, including Jupiter and Saturn in our own system. Specifically, if ohmic heating, the deposition of energy from electric currents driven by atmospheric dynamics interacting with the planet's magnetic field, is the dominant inflation mechanism, this tells us about the electrical conductivity of deep planetary atmospheres. If delayed cooling is dominant, it tells us about the opacity of hydrogen-helium under high pressure. If tidal heating is significant, it tells us about the dissipative properties of gas planet interiors. Each proposed mechanism requires specific interior properties. Testing which mechanism is correct through comparing theoretical predictions with observations of many planets across a range of masses, radii, ages, and stellar environments refines our knowledge of gas planet physics generally. The largest and most extreme planets provide the most extreme data points for testing these theories. They are the stress tests for our understanding. Let us now talk about a specific observation that is becoming possible with JWST that was not possible with any previous instrument, about the detection of individual molecular spectral lines in exoplanet atmospheres. Earlier generation instruments, Hubble's Wide Field Camera 3 in particular, could detect broad molecular absorption features in exoplanet atmospheres, features that span tens of nanometers of wavelength. This allowed identifying the presence of water, methane, and a few other molecules in relatively crude terms. JWST's Near-Infrared Spectrograph, NIRSPEC, and Mid-Infrared Instrument, MIRI, resolve features at much finer wavelength scales. Individual molecular rotation vibration spectral lines, the specific fingerprints that identify not just what molecules are present, but their physical conditions, temperature, and abundance. This is the difference between knowing a person is in a room because you can hear sounds, and knowing their name, age, and what they're saying because you can clearly make out their voice. For hot Jupiters, JWST is now routinely producing atmospheric spectra of such quality that atmospheric retrieval codes, computer programs that work backward from the observed spectrum to determine the atmospheric composition, temperature profile, and cloud properties, can be applied with high confidence. The results are revealing unexpected complexity. For WASP-39b, one of the best-studied hot Jupiters with JWST, the atmospheric composition shows evidence of disequilibrium chemistry, molecules present in abundances that are not what you would expect if the chemistry were in thermodynamic equilibrium. This implies active photochemistry and vertical mixing. The atmosphere is chemically dynamic, not static. For the largest planets, the ones with the hottest atmospheres and the most intense stellar irradiation, this chemical dynamism is even more extreme. Molecules are being created and destroyed rapidly by photochemical reactions. Thermal dissociation at high temperatures breaks apart molecules on the day side that reform as gas circulates to the cooler night side. This is atmospheric chemistry operating on timescales of hours, driven by the brutal stellar irradiation and the rapid day-night temperature contrast. Nothing like this exists in our solar system. JWST is revealing it for the first time. Let us now talk about the specific question of what the distribution of large planets tells us about the frequency of potentially habitable Earth-like planets. This is the question that connects the science of large exoplanets to one of humanity's deepest curiosities. Are we alone? The logic runs like this. We now know from Kepler statistics that Earth-sized planets in habitable zones are common. Estimates range from about 10 to 50% of Sun-like stars having an Earth-sized planet in the habitable zone. Even at the conservative end, 10% of the estimated 100 billion Sun-like stars in the Milky Way, this implies 10 billion potentially Earth-like planets. But commonness of Earth-sized planets in habitable zones does not immediately translate to commonness of Earth-like worlds in the sense that matters for life. Worlds with liquid surface water, active geology, long-term climate stability. This is where large planets enter the picture. The presence or absence of a Jupiter analogue in a planetary system appears to matter for the inner planets. Jupiter plays at least 3 distinct roles in our solar system's evolution. First, clearing debris. Jupiter's gravity scattered much of the leftover material from planet formation, asteroids and planetesimals, either into the asteroid belt, where Jupiter's resonances prevent them from accreting into a planet, or out of the inner solar system. This reduced the rate of large impacts on Earth over the past few billion years, creating a more stable environment for life to develop. Second, delivering water. Paradoxically, Jupiter may also have been responsible for delivering some of the water and organic material to early Earth. It scattered water-rich bodies from the outer solar system into the inner system during a period of orbital instability roughly 4 billion years ago. Third, architectural influence. The presence of Jupiter at 5.2 astronomical units with its specific mass appears to have been important for allowing Earth to remain on a stable, low eccentricity orbit. In systems without a Jupiter analogue, terrestrial planets may be more likely to be scattered onto eccentric orbits that periodically bring them closer to or farther from their star, disrupting climate stability. We do not know how sensitive these effects are to the specific properties of the Jupiter analogue. Does the Jupiter analogue need to be within a factor of 2 of Jupiter's mass? Does it need to be at a specific orbital radius? These are open questions that require better statistics on Jupiter analogue populations. But the directional result seems clear. Systems with cold Jupiters on wide orbits, systems resembling ours in this specific way, are somewhat more likely to have stable, habitable inner planets than systems without. Since cold Jupiters occur around roughly 10 to 15% of Sun-like stars, and hot Jupiters, which likely destroyed inner planetary systems during their migration, around only 1%, the majority of Sun-like stars do not have a direct Jupiter analogue. What fraction of those might still have habitable inner planets is a question that Plato and future radial velocity surveys will address. Let us now talk about what the study of the largest planets reveals about the formation of our own solar system, and specifically about the history of Jupiter itself. Jupiter is not a hot Jupiter. It did not migrate all the way inward to a sub-10-day orbit. But did it migrate at all? The answer appears to be yes, but it migrated inward and then back outward. This scenario, sometimes called the Grand Tack, was proposed by Kelvin and colleagues in 2011. In the Grand Tack model, Jupiter formed at about 3 to 4 astronomical units from the Sun. As the solar nebula gas disk was still present, Jupiter began migrating inward, the same mechanism that drives hot Jupiters all the way to their final positions. Jupiter migrated inward to about 1.5 astronomical units, inside the current orbit of Mars. But then Saturn formed. When Saturn's orbital period became twice Jupiter's, entering a 2-to-1 orbital resonance, the gravitational coupling between them reversed the migration. Instead of continuing inward, both Jupiter and Saturn began migrating outward. Jupiter eventually reached its current position at 5.2 astronomical units. Saturn ended up at 9.5 astronomical units. This outward migration dramatically reshaped the inner solar system. Before the Grand Tack, the region of the current asteroid belt was populated with planetesimals extending much closer to the Sun. Jupiter's inward and then outward migration scattered most of this material, explaining why the asteroid belt is so depleted compared to what formed there, and why Mars is smaller than expected. Much of the material that might have formed a larger Mars was scattered by Jupiter's passage. The Grand Tack is a hypothesis. It is not established fact. But it is supported by several lines of evidence, and it connects the story of Jupiter's formation to the formation of the entire inner solar system, including Earth. The study of hot Jupiter migration, of planets that underwent the same inward migration but without Saturn to reverse it, gives us observational data about how these migration processes work. Every hot Jupiter we study is a test of the migration models that also apply to Jupiter's own history. Let us now talk about something that makes the study of the largest exoplanets immediately practical, about the role of large planets in the search for biosignatures on smaller planets. When we search for biosignatures, chemical signatures of life, in the atmospheres of Earth-like planets, we face a major observational challenge. Earth-sized planets are small. Their atmospheres are thin. The signal of atmospheric absorption during transit is weak, roughly 10 times weaker than the signal from a hot Jupiter. The techniques being developed and validated on hot Jupiters, transit spectroscopy, emission spectroscopy, phase curve analysis, high-resolution spectroscopy, are exactly the techniques that will be applied to Earth-like planets when the instruments are sensitive enough. Hot Jupiters are the training ground. They are the bright, easy targets that let astronomers develop, test, and refine the methods. The discovery of sulfur dioxide photochemistry in the atmosphere of WASP-39b, the first detection of photochemical products in an exoplanet atmosphere, used methods and instruments that will be applied to smaller, fainter, potentially habitable planets in the coming years. Similarly, the detection of quartz crystals in WASP-17b's atmosphere demonstrated JWST's ability to detect solid particles, condensates, in an exoplanet atmosphere for the first time. This is directly relevant to detecting the kinds of complex mineral condensates and aerosols that might complicate the interpretation of spectra from Earth-like planets. Every unexpected discovery in the hot Jupiter domain, every strange spectral feature, every anomalous atmospheric composition, every surprise about how these atmospheres work, prepares us for interpreting the more subtle signals that will come from smaller, more interesting worlds. The largest planets are the pioneers of atmospheric characterization. The most habitable planets are the ultimate goal. Let us now talk about something that connects this entire conversation to the most personal human question about what it means to know these worlds exist. In all of human history before 1992, every human who ever lived had exactly 0 confirmed knowledge of planets beyond our solar system. The planets of our system were the totality of known worlds. 8 or 9, depending on when you were born, planets were the complete inventory of the universe's known planetary content. In a single human lifetime, 32 years, we have gone from 0 to over 5,000 confirmed exoplanets. From a sample of 8 to a sample of thousands. From a single known planetary system to a rich, diverse zoo of systems unlike anything we imagined. And among these thousands, the largest, the most enormous gas giants, the most extreme examples of what nature can produce when conditions allow, stand as the most visible, the most dramatic, the most immediately impressive evidence that the universe is vaster and more diverse than we can fully absorb. An object with a radius twice Jupiter's, orbiting its star in 3 days, with quartz crystals floating in its atmosphere and iron rain falling through its cloud decks. This is not a thing anyone imagined before 1995. It is not a thing that appears in the science fiction of earlier generations. It is stranger and more extreme than the imagination had reached. And it is real. Measured, confirmed, studied with the most precise instruments humanity has ever built. There is something worth pausing on in this. In one human lifetime, the inventory of known worlds has expanded from 8 to 5,000. The nature of those worlds has proven to be stranger and more diverse than our best theories predicted. The methods of detecting and characterizing them have advanced from uncertain wobbles in stellar spectra to detailed atmospheric composition maps. This is not done. This is barely begun. The next generation of instruments will expand the sample again and reveal yet more surprises. Future generations will look back at the discoveries of the 1990s and 2000s the way we look back at Galileo's discovery of Jupiter's moons, as the first steps into a territory that turned out to be incomprehensibly larger than the first explorers could see from where they stood. But right now, tonight, from wherever you are, you can look at a star and know it is not alone, that there are worlds around it, possibly including enormous gas giants larger than anything in our solar system, possibly including small rocky worlds with liquid water and life, possibly including things we have not yet imagined. The universe is full of planets, including some that are much, much larger than our largest. And we know this now, for the first time in all of human history, because a small group of people looked carefully at starlight and had the patience and the skill to read what it was saying. Let us now talk about the specific observational exercise that connects everything we have discussed to the night sky you can see tonight. Jupiter is your reference point for everything in this conversation. Find it. It is bright, white, steady, not twinkling. All the planets we have discussed are measured in units of Jupiter. Everything you know about the scale of these worlds starts with that one bright point. Then, look somewhere near it on the sky, any nearby direction, within a degree or two of Jupiter. Statistically, within that small region of sky, there are stars. And around some fraction of those stars, hot Jupiters are orbiting right now. Not detectable to your eye, not detectable to any ground-based amateur telescope, but present, orbiting in hours, heating to thousands of Kelvin, losing mass to their stars, inflated to radii that would dwarf our Jupiter. They are there, in that small patch of sky you can cover with your thumb held at arm's length. There are planets, enormous ones. Planets that have been measured and characterized and whose atmospheric composition has been determined by spectrographs on space telescopes. The sky is not a backdrop. It is not scenery. It is a dense, layered structure of stars and planetary systems, most invisible to your eye, all present and active and real. And among the most dramatic of those systems, the ones we have talked about tonight, are the largest planets humanity has ever found. Worlds that challenge our vocabulary for describing size. Worlds whose physical conditions have no analogue in our experience. Worlds that are real and measured and orbiting stars you can see right now. Find Jupiter. Everything else is measured against it. And what we have found is much, much larger. Let us talk about something that makes the study of the largest exoplanets particularly relevant to understanding our own solar system's history. About the connection between hot Jupiter migration and the structure of planetary systems we observe today. When a gas giant migrates inward through a protoplanetary disk, it does not travel silently. It interacts with the disk in ways that leave marks on the final architecture of the system. Understanding these marks lets us read the migration history of a system from its current state. As a gas giant migrates inward, it opens a gap in the disk, a ring of reduced gas density along its orbital path. This gap is maintained by the balance between the planet's tidal torques, pushing material away from the orbit, and viscous processes in the disk, trying to fill the gap back in. The width of the gap depends on the planet's mass. More massive planets open wider gaps. Inside the gap, disk material is depleted. Outside the gap, material is also affected. The planet acts as a barrier to the inward flow of material from the outer disk. This can starve the inner disk of material needed for planet formation in the inner system. As the planet migrates inward, it pushes this gap inward with it. Inner disk material can be swept inward ahead of the migrating planet, potentially being accreted onto the star. Or it can be pushed into resonances with the migrating planet, creating compact groups of small planets that move together. This migration-driven shepherding of inner disk material may explain a curious feature of hot Jupiter systems. They almost never have close companions. In contrast to systems without hot Jupiters, where multiple small planets on compact orbits are common, hot Jupiter systems are typically lonely. The hot Jupiter sits there, massive, close to the star, with nothing nearby. The likely explanation: the hot Jupiter's migration cleared the inner system. Anything that was forming interior to its final position was either accreted by the planet, pushed into the star, or ejected from the system during the violent gravitational interactions of migration. This has a direct implication for habitability. Hot Jupiter systems probably do not have Earth-like planets in their habitable zones. The migration that produced the hot Jupiter would have destroyed anything forming in the region where liquid water is possible. Cold Jupiter systems, like ours, tell a different story. The gas giant that stayed on a wide orbit did not migrate destructively through the inner system. Inner rocky planets could form and survive. Earth is an example. The statistical connection between the architecture of the outer system, hot Jupiter versus cold Jupiter versus no gas giant, and the inner system, presence or absence of potentially habitable rocky planets, is one of the most actively studied questions in exoplanet science. Getting the statistics right requires large samples, which is why surveys like those of the Plato mission and future radial velocity programs matter so much. Let us now talk about a specific phenomenon that is one of the most directly observable consequences of the size of the largest planets, about stellar contamination during transit, and what it teaches us about measurement precision. When a planet transits its star, it blocks a fraction of the starlight proportional to the ratio of the planet's cross-sectional area to the star's cross-sectional area, our planet over our star squared. For our Jupiter transiting the Sun, this ratio would be about 1/10 squared equals 0.01, a 1% dip in brightness. For a planet with a radius of 2 Jupiter radii transiting a Sun-like star, 2/10 squared equals 0.04, a 4% dip. This is a very large, easily detectable signal. The largest hot Jupiters produce transit depths of 2 to 4%, visible in high-quality photometry as clear, deep, well-defined light curves. This is one reason the largest planets were among the first detected by transit surveys. Their signal is large. The measurement is relatively easy compared to smaller planets. But large planet transits also reveal stellar physics in interesting ways. Stars are not uniform disks of constant brightness. Their surfaces are covered in granulation, faculae, star spots, and other inhomogeneous structures. A transiting planet passes in front of different parts of the stellar disk as it crosses, and the precise light curve shape depends on what structures are beneath the planet at each moment. When a transiting planet crosses a star spot, a cooler, darker region on the stellar surface, the transit depth temporarily decreases because the planet is now blocking less flux than average. The spot was already dark. This appears as a brief bump in the transit light curve. When a transiting planet crosses a facula, a brighter region, the opposite occurs. For large planets, these spot-crossing events are clearly visible in the light curves. They provide information about the latitudinal distribution of star spots on the host star, which tells us about stellar magnetic activity. This cross-contamination between planetary science and stellar science is an example of how the transit method extracts multiple types of information simultaneously. We are learning about the planets, but we are also learning about the stars they orbit. Let us now talk about a specific type of large planet that we have not yet discussed in depth, the superpuffs, and what makes them the most physically baffling objects in the exoplanet catalogue. Superpuffs are planets with densities even lower than the inflated hot Jupiters we have discussed. They have radii comparable to Jupiter or larger, but masses much smaller, leading to mean densities so low that they challenge our understanding of planetary structure. Kepler 51b is perhaps the most extreme example. Mass about 0.042 Jupiter masses, roughly 14 Earth masses. Radius about 0.636 Jupiter radii. This gives a mean density of about 0.03 grams per cubic centimetre. This is about 3% of the density of water. It is about 30 times less dense than styrofoam. It is barely denser than aerogel. Kepler 51b is a planet that seems like it should not be able to maintain itself. At such low density, the outer atmosphere should be escaping rapidly. The planet's gravity is barely sufficient to hold its own gas. What explains this? Several possibilities. The planet may be losing mass so rapidly through photoevaporation that what we observe is a transient state. Kepler 51b caught in the process of losing its atmosphere quickly and transitioning toward a denser, smaller final state. On timescales of tens to hundreds of millions of years, Kepler 51b may shrink dramatically. Alternatively, the planet may have an enormous, dusty or hazy upper atmosphere that makes its apparent radius much larger than the actual planetary body beneath. If the optically thick atmosphere extends far above the actual dense planetary interior, the transit gives a radius that reflects the top of the haze rather than the planet itself. The actual dense planet is much smaller, hidden beneath. JWST observations of Kepler 51b and similar superpuffs are beginning to test these hypotheses. The atmospheric spectrum can distinguish between a truly diffuse planet and a dense planet with a high, hazy upper atmosphere. Early results suggest the haze hypothesis may be correct, but this is still being worked out. Superpuffs represent the extreme end of a continuum of inflated planets. The largest hot Jupiters are somewhat inflated. The superpuffs are dramatically, mysteriously inflated. Understanding the mechanism that produces superpuffs will illuminate the physics of all inflated planets. Let us now talk about what happens in the long-term future of a system containing a hot Jupiter, about the stellar evolution perspective. Stars evolve. Our Sun, in about 5 billion years, will exhaust its hydrogen fuel and expand into a red giant, engulfing Mercury, Venus, and possibly Earth in the process. Similar evolution happens to all Sun-like stars. For hot Jupiter host stars, this evolution has interesting consequences. As the star expands into a red giant, the planetary atmosphere, already inflated by stellar irradiation, is now exposed to vastly increased luminosity. The atmospheric mass loss rate increases dramatically. the planet loses mass even faster than before. If the red giant expands sufficiently, as it swells to hundreds of times its current radius, it may engulf the planet's orbit entirely. The planet spirals inward through the tenuous outer layers of the red giant, experiencing ram pressure drag that further reduces its orbit. Some hot Jupiters will be consumed by their expanding host stars. Others will spiral inward and merge with the stellar core before the star fully expands. Still others, on slightly wider orbits, may survive the red giant phase, though greatly reduced in mass from the intense radiation and thermal ablation. The aftermath: a white dwarf, the dense remnant of the red giant's core with no hot Jupiter. Or a white dwarf with a surviving diminished planetary body in a tighter orbit than before. Some white dwarfs show heavy element contamination in their atmospheres: calcium, silicon, iron, magnesium, elements that are heavy enough to sink out of sight rapidly in the white dwarf's intense gravity. The only way these elements stay visible is if material is continuously being delivered to the white dwarf's surface. The material is coming from disrupted planetary bodies, rocky cores or metal-rich asteroids being tidally disrupted and accreted. The white dwarfs polluted by planetary material are the endpoints of planetary systems that ran their full course. The giant planets disrupted the smaller bodies, which then fell into the white dwarf. By studying the chemical composition of white dwarf pollution, what elements are present in what abundances, we can reconstruct the composition of the planetary material that was accreted. This is a completely different way of studying exoplanet compositions, not from the spectra of the planets themselves, but from the chemical signature they leave on their stellar remnant after the system's evolution is complete. Let us now talk about a specific discovery that exemplifies how the study of large planets contributes to understanding planetary system formation in ways not anticipated at the start, about planets in binary star systems. About half of all Sun-like stars are members of binary systems, two stars orbiting each other. For a long time, it was uncertain whether planets could form and survive in binary systems. The gravitational environment is more complex, with both stars perturbing the protoplanetary disk and potential planetary orbits. The answer, from observations, is yes. Planets exist in binary systems, and some of the most interesting large planets are found there. There are two configurations: circumbinary planets, orbiting both stars, and circumstellar planets, orbiting one star with the other star as a distant companion. The most famous circumbinary planet, Kepler-16b, is a Saturn-sized planet orbiting both stars of a binary system. It orbits the center of mass of the binary, outside both stars' orbits. It has two suns. Its sky would feature a binary sunset, where two stars set together, or at different times, depending on the orbital phase. This system inspired the twin suns of Tatooine, though that is a fictional desert world, while Kepler-16b is a Saturn analogue. The largest circumbinary planets discovered reach a few Jupiter masses. Their formation is complicated by the dynamical environment. The binary stars stir up the disk material, making it harder for solid bodies to collide and stick, rather than collide and fragment. Despite this, formation evidently occurs. The precise mechanism remains an area of active research. Circumstellar planets, planets orbiting one star in a binary, exist with the other star at distances of tens to thousands of astronomical units. For systems where the stellar companion is distant, thousands of astronomical units, the effect on inner planetary formation is small. For systems where the companion is closer, tens to hundreds of astronomical units, the Kozai-Lidov mechanism we discussed, which can tilt and eccentric a planet's orbit, becomes important. Several hot Jupiters have been found in binary systems where the stellar companion's Kozai-Lidov influence could explain the hot Jupiter's production. The planet formed on a wide orbit. The stellar companion perturbed it to high eccentricity and inclination, and then tidal interaction with the host star circularized the orbit at a short period, producing the hot Jupiter. This is one of the mechanisms for producing hot Jupiters that does not require disk migration. It is an alternative path to the same destination. Let us now talk about what is currently understood about the atmosphere of a planet that represents a bridge between hot Jupiters and directly imaged planets, about the atmospheric characterization of the intermediate class of warm Jupiters. Warm Jupiters are gas giants with orbital periods between roughly 10 and 200 days, warmer than cold Jupiters like ours, cooler than hot Jupiters. They are in an intermediate regime, both physically and in terms of observational accessibility. The atmospheric temperature of warm Jupiters, roughly 600 to 1200 Kelvin, is an interesting range because it is where many atmospheric chemical reactions are temperature sensitive. Some molecules that are stable at lower temperatures dissociate at higher temperatures. The balance between different chemical species is particularly sensitive to temperature in this range. JWST has begun characterizing warm Jupiter atmospheres with results that are already revealing unexpected complexity. The atmosphere of WASP 107b, a warm Jupiter with an exceptionally low density, making it a superpuff by some definitions, was characterized in detail in 2023. JWST detected sulfur dioxide, water vapor, carbon dioxide, and sulfur-bearing species. But the most striking finding was the detection of sulfur dioxide, confirming that photochemistry occurs in warm Jupiter atmospheres just as in hotter Jupiters, and additionally, the absence of ammonia.
Ammonia was expected at these temperatures based on equilibrium chemistry models. Its absence implies active mixing in the atmosphere, bringing material from deeper, hotter layers where ammonia has already been thermally destroyed. This disequilibrium, chemistry driven away from equilibrium by physical transport processes, is a key signature of active atmospheric dynamics. A dynamically active atmosphere mixes material vertically, preventing chemical equilibrium from being established. The specific pattern of disequilibrium observed tells us about the mixing timescales and the vertical structure of the atmosphere. For habitability considerations, disequilibrium chemistry is actually a positive sign. Earth's atmosphere is spectacularly far from chemical equilibrium. Oxygen and methane coexist, which is only possible because life continuously produces both. The detection of disequilibrium in exoplanet atmospheres is a marker of active processes, and active processes can include biology. We are not claiming this for warm Jupiters, they are not habitable. But the technical capability to detect disequilibrium chemistry demonstrated on warm Jupiters is exactly the capability that will be needed to detect the subtle chemical disequilibrium signatures of life on Earth-like planets. Let us now talk about the largest known planets in one more specific context, about what they tell us about the maximum possible size of a planet and why that limit exists where it does. The radius of a gas giant does not simply increase with mass. There is a surprising property. For objects between about 0.3 and 13 Jupiter masses, the radius is remarkably constant, hovering around 1 Jupiter radius with variations of perhaps 20 to 30%, excluding inflation effects. This is counterintuitive. We might expect that a more massive gas planet would be bigger. But the relationship between mass and radius for gas giants is weak and can even be inverted. More massive gas planets are in some cases smaller. The reason is that hydrogen and helium under high pressure behave differently from ordinary gases. At pressures of millions of atmospheres, electrons become delocalized. The material becomes conducting, and the pressure-density relationship changes fundamentally. More massive gas planets compress their interiors more, but the electrons resist this compression with quantum mechanical pressure. The net result is that adding mass to a gas planet compresses it almost as much as it adds volume, so the radius changes little. For the most massive planets approaching 13 Jupiter masses, the denser interior is nearly compensated by the electron degeneracy pressure. The radius is actually slightly decreasing with increasing mass at the very high end.
This is why brown dwarfs, which are much more massive than gas planets, are actually similar in radius to Jupiter, or even slightly smaller. The radius of a hydrogen-helium object is relatively insensitive to mass over a huge range of masses, from about a third of a Jupiter mass up to the stellar ignition threshold. The exceptions, the inflated hot Jupiters with radii of 1.5 to 2 Jupiter radii, are exceptions precisely because additional energy is being deposited in their atmospheres by stellar irradiation. Without this irradiation, they would be at roughly Jupiter's radius, regardless of their specific mass. This means that the largest planet by radius is not necessarily the most massive. It is the one that has been most effectively inflated by stellar energy input. The largest planets by mass are the ones closest to the brown dwarf boundary, compact, dense, and not particularly large. This counterintuitive result illustrates how gas giant physics is genuinely different from the intuitive notion that bigger means more massive. In this part of parameter space, physics works differently from ordinary, everyday intuition. Let us now talk about how all of this connects to a question that will be increasingly central to planetary science over the next decade, about the relationship between stellar metallicity, giant planet formation, and the prevalence of potentially habitable worlds. The correlation between stellar metallicity and hot Jupiter occurrence is one of the strongest observational results in exoplanet science. Stars with higher iron abundance are more likely to host gas giants. But what does this mean for Earth-like planets? Here, the picture becomes more complex. Some analyses suggest that Earth-like planets, rocky planets in habitable zones, do not show a strong preference for high metallicity stars. The rocky planet formation process seems more robust than gas giant formation. Small rocky planets can apparently form across a wide range of metallicities. If this is correct, high metallicity stars are more likely to have both gas giants and rocky planets. Lower metallicity stars are less likely to have gas giants, but may still have rocky planets at similar rates. For habitability, the implication is interesting. A high metallicity star system is more likely to have a Jupiter analogue, which provides the gravitational architectural benefits we discussed. But it is also more likely to have had a hot Jupiter that might have disrupted inner rocky planet formation. The net effect of metallicity on the prevalence of habitable worlds is therefore complex. There are competing factors. The current data is not sufficient to determine the balance conclusively. What we can say: the universe's first stars had essentially zero metallicity, all hydrogen and helium from the Big Bang. They could not form gas giants and could not form rocky planets because there were no heavy elements to make them. As successive stellar generations enriched the interstellar medium, first rocky planets became possible, then, with higher metallicity, gas giants became likely. Our solar system formed 4.6 billion years ago, when galactic metallicity had reached the right level for both rocky planets and gas giants. The specific metallicity of our Sun is what made both Jupiter and Earth possible. Systems that formed earlier in galactic history, with lower metallicity, may have Earth-size rocky planets but no Jupiter analogues. Systems that formed later, with higher metallicity, may have both, but with a higher rate of destructive hot Jupiter migration. We appear to be in a kind of Goldilocks zone of galactic chemical evolution. Not too early, no heavy elements; not too late, no additional benefits from higher metallicity but more disruptive migration, but at a time when the ingredients for both gas giants and rocky planets were available in the right proportions. The largest planets we have found, around high metallicity stars, massive, hot, close, are the product of conditions at the extreme end of this chemical evolution. They tell us about the upper reaches of what gas planet formation can achieve when given the most favourable conditions.
And they help us calibrate our understanding of the conditions that produced something more modest, but more important for life: our own Jupiter, our own Earth. Let us talk about something that ties together the physics of the largest planets with one of the most active areas of current research, about atmospheric escape and how studying the largest hot Jupiters has transformed our understanding of how planets lose their atmospheres over time. The process of atmospheric escape, gas leaving a planet permanently against the pull of gravity, operates on all planets with atmospheres. On Earth it is extremely slow. The escape rate of hydrogen from Earth's atmosphere is measurable but negligible over human timescales. On Mars, which has a thinner atmosphere and weaker gravity, the escape rate is larger, and over billions of years, Mars has lost most of its original atmosphere to space. For hot Jupiters, large gaseous planets extremely close to their host stars, atmospheric escape operates in a regime called hydrodynamic escape, or mass loss-driven photoevaporation. The stellar extreme ultraviolet and X-ray radiation ionizes and heats the upper atmosphere so intensely that the gas flows away from the planet as a continuous stream, not individual high-energy molecules escaping stochastically, but a bulk flow of atmospheric material. The observational signature of this is remarkable. Transiting hot Jupiters, when observed in ultraviolet wavelengths sensitive to hydrogen and helium, show a transit depth much larger than in optical wavelengths. The hot gas flowing away from the planet extends far beyond the visible atmospheric boundary, forming a comet-like tail trailing the planet in its orbit. The first detection of this extended atmosphere was made with the Hubble Space Telescope for HD 209458b in 2003. The hydrogen Lyman alpha transit depth was about 15%, compared to about 1.5% in optical. The planet's atmosphere extended out to several planetary radii, with gas flowing away from the planet at speeds of tens of kilometers per second. Subsequent observations detected helium escaping as well, detected through the 10,833 angstrom helium line in the near-infrared, more accessible from the ground than the ultraviolet Lyman alpha line. The detection of escaping helium by Jesus Spark and collaborators in 2018 opened a new observational window on atmospheric escape that ground-based telescopes can access. What does this have to do with the largest hot Jupiters specifically? The most massive hot Jupiters, those approaching 10 Jupiter masses, are more resistant to atmospheric escape than lower mass ones. Higher gravity holds the atmosphere more tightly. The escape rate is lower relative to the total atmospheric mass. Lower mass hot Jupiters, like WASP 17b with its half Jupiter mass but twice Jupiter radius, are far more vulnerable. Their low surface gravity cannot hold the puffed atmosphere against the intense stellar irradiation. The escape rate is high relative to the total mass. This creates a selection effect over time. Low-mass inflated hot Jupiters lose their atmospheres and shrink.
Over hundreds of millions to billions of years, they transition from gas giants to something smaller, perhaps a bare, rocky or metal-rich core, perhaps a water-rich sub-Neptune. The distribution of planet sizes observed by Kepler shows a curious gap, a range of radii between about 1.5 and 2.0 Earth radii, where there are relatively few planets. This has been interpreted as the photo-evaporation valley. Planets in this size range started as slightly larger sub-Neptunes or mini-Neptunes, lost their hydrogen envelopes through photoevaporation, and ended up as smaller, bare, rocky planets. The gap is the transition zone being depleted. Hot Jupiter photoevaporation is the extreme version of the same process that creates this valley in the smaller planet population. By studying the most dramatic atmospheric escape from the largest, most irradiated hot Jupiters, we calibrate the physics of atmospheric escape that then applies to smaller planets. This is another instance of the general principle. The largest and most extreme exoplanets are the natural laboratories for the physics that matters across the full planetary population. Let us now talk about a specific measurement that has become possible with modern spectrographs, and that provides some of the most direct information about hot Jupiter atmospheres, about wind speed measurements through the Doppler shift of atmospheric spectral lines. The concept is elegant. In a tidally locked hot Jupiter, the dayside atmosphere is heated to high temperatures and the night side is cooler. The temperature gradient drives winds. The atmosphere flows from the hot day side towards the cooler night side, carrying heat. These winds move at high speed, in some cases several kilometers per second, comparable to a small fraction of the escape velocity. As the planet transits, the part of the atmosphere on the leading limb, the part first entering the stellar disk, is moving toward us, blue-shifted, while the part on the trailing limb is moving away, red-shifted. By measuring the Doppler shift of specific molecular spectral lines during transit, comparing the blue-shifted limb to the red-shifted limb, we can directly measure the wind speed. This has been done for several hot Jupiters using high-resolution spectrographs on large ground-based telescopes. The HARPS spectrograph at the 3.6-meter ESO telescope and Espresso at the VLT have detected Doppler signatures of atmospheric winds in hot Jupiter atmospheres. The measured wind speeds are typically 1 to 5 kilometers per second, comparable to the fastest winds in our solar system, on Neptune, where winds reach about 0.6 kilometers per second. The wind direction inferred from the Doppler measurements is consistent with the expected superrotation, the atmosphere rotating faster than the planet itself, driven by the day-night temperature contrast. For the largest hot Jupiters, with their most extreme temperature contrasts, the wind speeds are predicted to be largest. At temperature contrasts of 2000 to 3000 Kelvin between dayside and nightside, the pressure gradient driving the atmospheric circulation is enormous. The resulting winds approach 10 kilometers per second in some models. These wind speeds have implications for the transport of heat and chemical species around the planet. A wind at 5 kilometers per second circulating a planet with a circumference of perhaps 400,000 kilometers, comparable to HAT-P-67b, could complete a circuit in about 22 hours. This means the chemical composition of the atmosphere is being continuously mixed on timescales comparable to the orbital period, creating the chemically dynamic, non-equilibrium atmospheric state that JWST is beginning to characterize. Let us now talk about the role of tides in sculpting the orbits and rotation states of the largest planets, because tidal physics is central to understanding why hot Jupiters are where they are and how they behave. Tides are differential gravitational forces.
The gravitational attraction of one body on the near side of another body is stronger than on the far side, creating a stretching effect. For Earth and Moon, this produces the ocean tides and the gradual recession of the Moon from Earth. For hot Jupiters and their host stars, the tidal forces are much larger in relative terms because the planets are so close. Tidal locking, the synchronization of a planet's rotation period with its orbital period, is a direct consequence of tides. When a planet is close enough to its star, the tidal bulge raised by the star on the planet experiences a gravitational torque that gradually slows the planet's rotation, if it was initially rotating faster than its orbital period, until rotation and orbital period are equal. At this point, the same face always points toward the star, as our Moon always shows the same face to Earth. All known hot Jupiters are believed to be tidally locked. Their orbital periods of 1 to 10 days and their proximity to their stars make tidal locking essentially certain over the system lifetime. This is why we speak of permanent dayside and nightside. The geometry is fixed. But tides do more than lock rotation. They also transfer angular momentum between the orbital motion and the rotation of the star. As the planet orbits faster than the star rotates, which is the case for most hot Jupiters, the tidal bulge raised on the star by the planet leads the planet slightly in longitude. This offset bulge exerts a gravitational torque that decelerates the planet's orbit and accelerates the star's rotation. This process is slow, operating on timescales of billions of years for typical systems. But for the closest hot Jupiters, WASP 12b, TOI 2109b, it is measurable. The orbital period is decreasing at rates that can be detected with years of transit timing observations. The total angular momentum of the star-planet system is conserved. What the planet loses, orbital angular momentum as the orbit decays, the star gains, rotational angular momentum. Young stars hosting hot Jupiters should be rotating somewhat faster than similar stars without hot Jupiters, because the hot Jupiter has been spun up the star over the system lifetime. Some observational evidence supports this. Hot Jupiter host stars show a slight tendency toward faster rotation than stars without hot Jupiters at similar ages, consistent with spin-up by tidal interaction. This is a subtle effect, not always distinguishable from the natural spread in stellar rotation rates, but statistically present. The eventual fate of the orbital decay is the planet's demise, as we discussed for WASP 12b. The characteristic timescale of this orbital decay depends on the tidal dissipation quality factor, Q, of the star, which quantifies how efficiently the star dissipates tidal energy. Despite decades of theoretical work, the value of Q for Sun-like stars is poorly constrained. It depends on the internal structure of the star and how the tidal waves propagate through it. Measuring the orbital decay rate of multiple hot Jupiters around stars of known properties gives us observational constraints on Q, a direct measurement of stellar tidal physics. This is another case where studying exoplanets teaches us about stellar physics. Let us now talk about something that illustrates how discoveries about large planets cascade into unexpected directions, about the connection between hot Jupiter research and the understanding of stellar magnetic activity cycles. The Sun has an approximately 11-year magnetic activity cycle, the sunspot cycle. At solar maximum, the Sun has many sunspots, increased ultraviolet and X-ray emission, and more frequent coronal mass ejections. At solar minimum, the surface is quieter. Stars in general have magnetic cycles of various periods, driven by the stellar dynamo, the interaction between rotation and convection in the stellar interior. Now, several hot Jupiter host stars show chromospheric activity, emission from the stellar chromosphere in certain spectral lines, that is modulated at the planet's orbital period,
rather than the stellar rotation period. The stellar activity is somehow synchronized with the planet's orbit. The most studied case is Tau Boötis, one of the nearby hot Jupiter hosts visible to the naked eye that we mentioned. Tau Boötis b orbits every 3.3 days. The stellar chromospheric activity shows a modulation at this 3.3-day period rather than, or in addition to, the stellar rotation period. The interpretation: the hot Jupiter's magnetic field is interacting with the star's magnetic field. The planet orbits inside the stellar magnetic field. It is embedded in the corona. As it orbits, the interaction between the planetary magnetic field and the stellar field creates a kind of magnetic wake or magnetic flux tube connecting the planet to the stellar surface. This connection modulates the stellar chromospheric activity at the orbital period. This is a phenomenon, magnetic star-planet interaction, with no analogue in our solar system. Jupiter is far enough from the Sun that the magnetic interaction is negligible. Hot Jupiters are inside the stellar corona, embedded in the stellar magnetic environment, and the interaction is significant. The study of hot Jupiter magnetic interactions with their host stars has opened a new area of research: star-planet magnetic coupling. What is the magnetic field of a hot Jupiter? How does it interact with the stellar field? Does the energy deposited in the stellar chromosphere by this interaction affect the stellar magnetic cycle? For the most massive hot Jupiters, those closest to 13 Jupiter masses, the magnetic field should be the strongest. These are the objects where star-planet magnetic interaction should be most significant. In the extreme case, the planet might actually influence the stellar magnetic activity cycle, creating a cycle that is partly driven by the planet rather than purely by stellar internal physics. This remains speculative for now, but the observation of stellar activity correlated with planetary orbital periods in several systems suggests the effect is real and worth investigating further. Let us now talk about what is perhaps the most profound implication of the discovery of thousands of exoplanets, including the largest ones, about what it means for our philosophical understanding of our place in the universe. Before exoplanet discoveries, we had one example of a planetary system. We could not know whether our solar system was typical or exceptional. We had no comparison. The principles of planetary formation we had were based on reverse engineering the system we lived in. We were, in a sense, reasoning from a sample of one. With 5,000 confirmed exoplanets, we have moved from a sample of one to a sample of thousands. And the lesson from this sample is unambiguous. There is no single template for a planetary system. There is no standard against which our solar system can be measured and found to be normal. Our solar system has no hot Jupiters. Roughly 1% of similar stars do. Our solar system has no super-Earths or mini-Neptunes, the most common type of planet in the galaxy. Our solar system has Jupiter on a wide, near-circular orbit, a configuration shared by perhaps 10 to 15% of similar stars. What does this mean? It means we cannot reason from our solar system to general principles without knowing where our solar system sits in the distribution of possible outcomes. We now have that distribution, imperfectly, with observational biases that we are still correcting for, but well enough to know that our system is not the median outcome. This is an important shift in perspective. Not that our solar system is special in a mystical or privileged sense, but that it is one specific outcome of a process that produces a very wide range of outcomes. And understanding why it has the specific configuration it does requires understanding the full range. The largest exoplanets, the hot Jupiters with radii twice Jupiter's, orbiting in hours with iron rain in their atmospheres, are part of this full range. They represent outcomes where conditions were different from ours. More material available, more efficient migration, more intense stellar irradiation. By understanding them, we understand more completely the range of what is possible. And by understanding the range of what is possible, we understand better why what exists in our solar system has the specific form it does, including why there is a warm, wet, biologically active Earth. The existence of the largest planets we have ever found is, paradoxically, part of the explanation for why we exist to find them. Let us now talk about the very specific sensory experience of the night sky that connects to everything we have discussed, about what looking at the sky actually means when you know what is out there. The night sky that you see, the stars, the faint glow of the Milky Way, the occasional planet, is not just a visual display. It is a projection of an enormously complex three-dimensional structure onto the sphere of your perception. Every star you see is different. Different mass, different temperature, different age, different chemical composition, different stage of its life. Many of them are binary or multiple systems. Many have planetary systems, some with gas giants, some with rocky planets, some with both, some with neither, that we have detected. Among those planetary systems, a fraction has planets larger than anything in our solar system. Gas giants with inflated atmospheres and short orbital periods. Gas giants with masses approaching the brown dwarf boundary. Directly imaged young gas giants cooling slowly from their formation heat, radiating in the infrared, visible to our telescopes but invisible to your eye. When you look at a star and know it has a hot Jupiter, as you know for Tau Boötis and 51 Pegasi, the star is not just a point of light anymore. It is a system. The point of light represents a sun with a large gaseous world orbiting it every few days, heated to thousands of Kelvin, losing mass to space, tidally locked with one burning face always toward its star. That reality is encoded in the point of light, not visible to your eye, but there, known, measured, understood to a level of detail that would have seemed impossible 30 years ago. This is what science does to the sky. It does not reduce it, it deepens it. A star is not diminished by knowing it hosts a giant planet. It becomes richer, more specific, more real. The sky you see tonight is populated with worlds. Thousands of confirmed planets around just the nearest and brightest stars. Statistically, hundreds of billions of planets throughout the Milky Way, including some of the most extreme environments that nature produces. The largest, hottest, most dynamically extreme planetary objects known. All of it happening right now, every night, whether you're looking or not. Tonight you are looking, and you know what is out there. Go outside tonight. Find Jupiter. It is the brightest steady point that is not the moon. White, unwavering, not twinkling the way stars do. Find it. Look at it for a moment. That is 318 Earth masses. That is an atmosphere where storms larger than Earth have raged for centuries. That is the gravitational anchor of our solar system, the body that shaped the orbits of everything around it, that deflected comets, that participated in the scattering events that built the inner solar system and delivered water to the early Earth. That is the largest planet you will ever see with your own eyes, and it is 1/13 the mass of the largest planets we have found. Somewhere in the direction of the constellation Pegasus, 51 light-years away, a distance so small in galactic terms that it is practically next door, there is a star slightly dimmer than what your naked eye can quite resolve under city lights. Around that star, every 4.23 days, a gas giant nearly half the mass of Jupiter completes an orbit. It is so close to its star that its atmospheric temperature exceeds 1,200 Kelvin. It has been there for billions of years. It will be there when the Sun becomes a red giant and Earth is gone. That planet changed science. When Michel Mayor and Didier Queloz announced its discovery in 1995, a gas giant where no gas giant should be, orbiting in 4 days what should take years, the reaction was disbelief. The instruments must be wrong. The analysis must be flawed. Gas giants do not form close to stars. Everyone knew this, except nature did not know it. 51 Pegasi b was real. The instruments were right. The analysis was correct. The theory was incomplete. And from that single discovery, one planet around one unremarkable star, just visible to the naked eye in the square of Pegasus, everything changed. In the 29 years since, we have found 5,000 more, and among those 5,000, we have found things that make 51 Pegasi b look conservative. HAT-P-67b, almost 3 Jupiter radii across, so puffed by stellar irradiation that its mean density is less than 1/10 of water's, orbiting in 4 days, losing mass continuously to space. A planet so large and so diffuse that it barely qualifies as a solid notion in the traditional sense. TOI-2109b, 5 Jupiter masses orbiting in 16 hours, 1 orbit per sleeping period, surface temperature of 3,630 Kelvin, hotter than many stars. Its orbit is decaying. In a few million years, it will fall into its star. We are watching it in the final chapter of its existence. WASP-12b, spiraling inward, losing hundreds of thousands of tons of atmosphere per second. Its orbital period decreasing by 29 milliseconds per year, measurable, confirmed, a death clock ticking in the data. In 10 million years, gone. WASP-17b, retrograde, orbiting its star backwards relative to the star's own rotation. Clouds made of quartz crystals floating in the atmosphere, iron condensing in the cooler upper layers raining inward, a world where the weather is made of molten rock droplets and silicate crystals. HR 8799, 4 gas giants orbiting a single star, all 5 to 7 times Jupiter's mass, all photographed directly, their orbital motion visible in images taken years apart. We can watch them move. Slowly, their orbital periods are decades to centuries, but measurably, visibly in the data. Kappa Andromedae b, 13 Jupiter masses at the boundary of what we call a planet, on an orbit at Earth's distance from its star. If it were here, where Earth is, it would be visible as a brilliant disk in the sky, and its gravity would have disrupted our orbit and ended everything. All of these are real, all of them measured, all of them orbiting their stars right now, tonight, as you stand outside and look up. The universe builds objects like this, routinely, consistently. Around 1% of stars there is a hot Jupiter, a massive, close, extreme world. In a galaxy of hundreds of billions of stars, that is, hundreds of millions of hot Jupiters. Hundreds of millions of worlds with iron rain and quartz clouds and orbital periods shorter than Earth days. And yet from Earth, from this small rocky planet at a comfortable distance from a quiet star, all of that is invisible. The largest planets ever found are invisible to the naked eye. They are encoded in the wobbles of starlight and the depths of transits and the spectra of stellar atmospheres, information so subtle that extracting it required the development of instruments of extraordinary precision and the analysis techniques to interpret what those instruments found. We extracted it. In 29 years, from 0 to 5,000 worlds. Look at Jupiter again. The scale of what we have found goes from that point of light, enormous by human standards, 11 times Earth's radius, 318 times Earth's mass, to objects 13 times more massive. The range of planetary sizes in the universe is vastly larger than anything our solar system prepared us for. And the largest planets exist in conditions that make the word hostile sound inadequate. Temperatures where rock is vapor. Pressures that crush matter into exotic metallic states. Magnetic fields strong enough to interact magnetically with the host star. Orbital speeds where a year passes in hours. Mass loss rates where the planet literally evaporates, the material streaming away toward the star like smoke from a dying fire. Nature does all of this, not in theory, in practice, in real systems orbiting real stars that you can find on a star map and look at through a telescope. The night sky that appeared to our ancestors as a fixed vault of stars, the same positions, generation after generation, turns out to be a deep, layered structure crowded with planetary systems. Most invisible, all real, all operating according to the same physical laws that govern everything on Earth: gravity, thermodynamics, electromagnetism, nuclear physics, but in conditions so extreme they produce phenomena with no terrestrial analogue. Iron rain, quartz clouds, orbits measured in hours, atmospheres glowing at stellar temperatures. All of it in a galaxy you live in. You belong to a species that learned to read this. That took the wobble of starlight and the dimming of a distant sun and extracted from them the existence, the mass, the radius, the temperature, the atmospheric composition of worlds hundreds of light years away. 29 years from the first discovery to 5,000 confirmed planets and detailed atmospheric spectra from a space telescope that did not exist when the first planet was found. Go back inside tonight knowing what is out there. The sky is not empty, it is full of worlds larger than anything we imagined, and we found them.